Okay, good morning, everybody. Welcome to my talk about the pre-development project we did at TrueDyne Sensors the last few years. It's about the MEMS sensor to analyze combustion gases, natural gas with hydrogen. And yes, I'm happy that some people find the way to this forum. And I will talk about TrueDyne first. So TrueDyne is we are a small company with 12, 13 people belonging to a big company, Anderson Hauser, but we are focusing on physical sensors, miniaturized MEMS-based sensors, typically for properties of liquids and gases like density, viscosity, and from these parameters, we can deduce concentration of quality information of these gases. So we have some motto, rethink sensing. So we try to take existing sensors and recombine them and give new sensor outputs. The aim is to have quality information in the process. So we want to measure directly in the process at process conditions and not to have complex gas or liquid handling systems to come to the sensors so we want to go into the process and go into commercialized industrialized products. This is our sensor portfolio we have. You will find us in the main line. So we are booth 325. So you can see all these sensors. Today, so you see we have density sensors, viscosity sensors, flow sensors for liquid and gases. And today I will talk about this last sensors, this MGC, which is a sensor for gases, which measures density, viscosity, concentration, calorific value of gases. So what is our principle to go? So we have mainly resonating sensors. So we have some resonator, a MEMS, a small resonator. I will show you some examples of this. And then we have some electronics, which move this resonator to resonant, measures the natural frequency, the quality factor. And then we have a model, a sensor model to calibrate these output values to fluid properties like density, viscosity, or temperature, pressure, thermoconductivity, specific heat capacity. And then we have a second model in our electronics, which is a customer model, an application model. It can be quite diverse. So from density, viscosity, you can find a lot of different applications. And so my role is somehow to these models. So I'm working on these models. So, and then I will show you how we did it in this example here. You see the chip, you will find it later in other slides. So, but these are other chips we have. So this was the first chip. This is a tiny MEMS tube, which is like a flow meter, like a Coriolis flow meter. So the liquid or the gas will flow through this tube. The tube is resonating, and if you have, you know, the physical lesson of harmonic oscillator, so you have a stiffness of the tube, and the liquid will give added mass. So the heavier the liquid, or the more dense the liquid, the mass becomes bigger and the frequency goes lower. So that's the basic concept of density sensors. Viscosity is a bit more complex. Then you have some damping effects, but you can imagine that if you put this in liquid, it will be damped and the frequency will also changed. And this is somehow in this physical model we have for each sensor. This chip is placed in a industrialized sensor like this. You have the chip here, you have a fluidic input, output, you have electronics and MOPOS output at the on a cable, and you can combine this with a pressure sensor. This sensor works for liquid and gases, so together with the pressure sensor, it gives a nice gas density sensor, which can be used in a wide temperature range, -40 to 60, even 80 degrees, 0 to 20 bars. We typically use it for binary mixtures or in process application like welding gases, mixture of nitrogen with helium, or at modified atmospheric packaging of salad bowls and so on. We have another sensor. So we are a Swiss company, and in Switzerland we have these watches, and not only the mechanical watches, but also the quartz watches. And we use a quartz tuning fork from Swatch. We opened the case, and we can use that as a very low cost gas density sensor. This is how it looks. So we added the pressure sensor. On the other side is the very tiny tuning fork. And as well, we have electronics. We have a case. You can screw this into directly into a pipe or flow through this case. And but you can use it also as it is, only the PCB, you screw it, you put it somewhere in the gas. And then you have again a MOPOS output with your sensor signals. This is again used in typical process gas application where you have two gases or maybe three, with you know, the two, and you want to have the concentration of the third gas. Typically binary mixture or clean gas detection. You can detect on a gas bottle, is it oxygen or is it nitrogen or is it CO2, so that nobody can connect the wrong bottle to somewhere. So we use it on the big gas trucks. That's not the big gas truck does not load the wrong gas. So okay, but these two sensors can only measure density. So what is the problem behind that is, if you want to really distinguish between gases without input, you need more dimensions. And the first dimension we like to open was the viscosity. If you have density and viscosity, you can distinguish between, for example, ethane and nitrogen. With density, you cannot, not good. And the talk was about natural gas, and natural gas typically is methane, ethane, propane, but also nitrogen and CO2. So with only density, we have to, you have to know how much nitrogen is in it. Otherwise, you or have nearly no nitrogen. Like when you have LNG, you have typically low nitrogen inputs, then density is maybe enough, but for typical applications, not. So you need viscosity, and when you would have viscosity, you could distinguish between inert gases like nitrogen and CO2 and combustion gases. This is the first concept. I can show it in another way. So this is a plot of molar mass, which is basically the density of the gases and calorific value. And you see even hydrogen fits nicely to these combustion gases, but nitrogen and CO2 not. So density is not enough. If you plot the same gases on a plot with Wobbe index, which is the calorific value divided by the square root of the specific gravity, then you can plot nitrogen, methane, ethane, propane, butane on one line with viscosity. CO2 fits quite good, but not that perfect at nitrogen, and only hydrogen is not perfect. So we need a third parameter if we have hydrogen as well in this combination, and therefore we need the thermal conductivity. So thermal conductivity from hydrogen is quite different to the other gases. If you have no helium, what I would expect if in a pipeline, not at the borehole, but in a pipeline, you have no helium, so you can really thermal conductivity is a good measure to get the concentration of hydrogen. Here you see just a correlation of just basically thermal conductivity of natural gas with hydrogen with the content and high hydrogen content. So it correlates quite nicely. So this brought us to the development of this chip, which is able to measure density, viscosity, and thermal conductivity in temperature on one chip. We use micro cantilever. So these are very, maybe here you have the dimensions. So the length of the cantilever is about 500 to 600 micrometers. The thickness is 5 micrometers. So it's a really tiny cantilever, so that it's basically quite damped even in low pressure gases. So that we have information of the damping. You can imagine in this animation that the cantilever will be damped through to the viscosity of the fluid. So you can measure by exciting these cantilever with piezoelectric transducers. Can measure frequency and Q factor, and from this deduce density and viscosity. Then additionally, we have a temperature measurement directly on the cantilever. So we know exactly the gas had this temperature. It's very important to know the exact temperature of the gas where you measure these thermophysical properties. And last but not least, we have 2 heaters on each cantilever. So we can heat one cantilever and measure temperature difference between the two. And from this, we can also deduce thermal conductivity and even heat capacity if you do the heating not steady. So it's really a sensor which gives a lot of information in a size of 4 to 4 millimeters. So now I will show some experimental tests we did. So we placed this chip on a PCB. We protected it. It's quite important to protect the chip with somehow a diffusion. So we use a sinter filter, a bronze sinter filter protection to allow quick gas diffusion. So it's a tiny cell. Within 1 second, the diffusion is done, but you have no convection. So you can place this chip directly in the flow and even measure under steady state condition thermal conductivity without convection. due to this filter. Then we have a pressure sensor. That's the only information our sensor gives not. And with this, we can go directly in a line. So we have this, we use this cylinder where we could connect it fluidically on one side and electrically on the other side. And then this is a typical setup where we did the first test in a chamber where you can mix gases. So here you see the cylinder. You have here a mass flow control to control the gas which flows through. And what you see here is the electronics we use. So it's quite bulky right now, and this is the work of this year. So we want to shrink this electronic as well, because the chip is now very tiny. But to show the proof of principle, it's okay with this electronic. And I show you some results with it. We did a lot of testing last year and this year. This is basically 7 mixtures, gas mixtures in a range from 0 to 20% hydrogen. We have inert gases up to 4% nitrogen and 4% CO2. And then the rest is just typical natural gas mixtures. We tested these 6 gases in different pressure and different temperatures, so a range of 0 to 50 and 2 to 6 bar. So how we did it, we took these bottles and placed the sensor in an oven and changed the pressure and the temperature. And now these are the results. As you remember the models, we have first a calibrated sensor. So the first is to get density. You see, we measure density. That's the error in kilogram per cubic meter. Density below 10 grams per cubic meter. So about 7 grams for all these gases, for all pressures, all temperatures. And then viscosity, here I plotted the relative error, 1% typically, plus minus is the accuracy of the viscosity measurement. And thermoconductivity, where we have about 0.5% relative error for all these gases, all conditions. This was the first method, calibrated sensor. Then for this application, that's somehow the customer model. We want to have a correlation model using these input parameters and outputting all the relevant values like the Wob index, calorific value, concentrations of inert gases, concentration of hydrogen, molar mass, and so on, of a natural gas with up to 30% hydrogen, up to 13% inert gases in a range of -20 to 60. So that's quite a universal model, which a lot of natural gas fits to that. And this is the output of the second model, so we can give out reference density at reference conditions, which is now in the range of about 3 grams per cubic meters, which means about 0.5% relative error for methane. Then Wob index, as you remember from viscosity and correlation, in the range of 1 to 1.5, all the gases were within this range. Overall temperature, so on the process condition, flowing gas at the temperature and pressure. Then if you know Wob index, you can calculate back to the calorific value. The accuracy is about the same, since the density we know quite accurately. Then you can calculate total inert content, inert gas content. So it means the sum from nitrogen and CO2, which we can measure in an absolute, in about plus minus 1% mole percent or volume percent. Here you see the same plot, and so we measured up to 8%. Here we had the gas with 4% CO2 and 4% nitrogen, and so on. And so you see the total inert gas content versus the range of inert gas content. And finally, the hydrogen concentration, we could measure it within about 0.3% absolute volume over the whole range. Again, the same plot against hydrogen concentration. You see we had gases with no hydrogen, with 1%, with 10%, with 20%. So this was somehow the proof of concept that our chip is able to measure under process conditions a quite complex gas mixture. We can give out the physical properties, measure them, and give out with a correlation model, reference density, Wob index, calorific value, total inert gas content, and hydrogen content. Additionally, we could also calculate methane number from these values. It would also be quite a nice correlation. This is somehow my conclusion and outlook. So we showed that we have a chip that is able to do that. This measurement, the chip design is aimed to be mass product. So we can imagine in some years that in every gas meter such a chip could be placed directly in the process. For this, we need to shrink the electronics. That's our main focus. And we will have, by the end of the year, demonstrate the kits available to be installed at customer sites. And if you're interested, visit us at the booth 325 or ask questions right now. Thank you. He has a question.
Yeah, thank you very much. My name is Christof from Fraunhofer IKDS, from Fraunhofer Society. Very interesting approach, but my question is about the algorithm, how you calculate the concentration from your signal. Is it something like artificial intelligence that you are measuring a lot of compositions and finding correlations because you have a lot of different components in the gas mixture?
Yes.
And you don't have so much distinctive signals. So how you make this color? How have you made this coloration?
So it's
correlation.
It's not. I don't use artificial intelligence for that. So you find some nice correlations. You do a lot. You can have a databases where you can calculate a lot of different mixtures and the parameters. So like NIST or so, you know the behavior, and then you find the physical correlations behind it. So it's more a linear regression based algorithm.
Okay, understood. So you have made a lot of calculations with simulated compositions, and then you have
tested it in real gases.
Yeah. And then you have deduced some logics how you extract the signals.
Yes.
Okay. Smart. Thank you.
Yeah.